This is question number 58 on page 555, which says these two resistors are placed like this. This is 8.8 ohms because that is a beautiful ohm symbol. 4.4 ohms, 0.36 microfarads, 0.48 microfarads. This is a switch, and these are all hooked to a 24-volt battery. And then with the battery switch open, we are supposed to find the potential at points A and B relative to the negative terminal, so relative to this point. And point A is right here, and point B is right here. Well, with the switch open, there's two loops here. There's a loop around here, and there is a loop around the outside. With the loop around there, we can see that these two resistors are actually in series, and so the equivalent resistance of those is 8.8 plus 4.4, which is 13.2 ohms. Now the reason that's important is because if I know the equivalent resistance, I also know the current, because these are getting that 24 volts. So V equals IR, but V is 24 and R is 13.2, so I know that the current through each one of those resistors is 24 divided by 13.2, or 1.8181. 1.81, and that 81 repeats forever, amps. That current flows through each resistor, and so if I want the potential difference from here to here, that's just the voltage drop across that resistor. All I need is the voltage times the current, and so, or sorry, not the voltage times the current times the resistance. So I can take 4.4 times 1.81 and get my voltage drop there, which is 8 volts. 8 volts. So there's 8 volts of potential difference between A and the negative terminal of the battery. We're also supposed to find that at point B. Well, again, with the switch open, these two capacitors are in series with that battery, and so what I want to find is the voltage drop across that resistor, or not that resistor, that capacitor. Remember, the voltage across a capacitor is given by, well, the charge in a capacitor is the capacitance times the voltage, so the voltage drop across that thing is the charge on the capacitor divided by its capacitance. I know its capacitance, so if I can find its charge, I can find the voltage drop across it, and then the voltage drop across there will be the same as the potential from the negative to B. So all I have to do on that is find the equivalent capacitance of those two capacitors, and those are in series, so I have 1 over 0.48 plus 1 over 0.36 inverse. And so if I do that, 0.48 inverse plus 0.36 inverse, and then invert that, I get 0.2057 equals 0.20, I'm going to call it 6, because these are in microfarads, this will also be microfarad. So 0.206 microfarads for the equivalent capacitance, CEQ. Now, that means the charge that's distributed on that equivalent capacitor, Q, is equal to the voltage that would get, 24 times that capacitance. So 24 times 0.206. 24 times 0.206 is 4.944 microcoulombs. 4.944 microcoulombs of charge. Now, remember, when these are in series, the charge here and the charge here and the charge here and the charge here are all the same, because this charge separation occurs because the charge on one plate is pulled around and put on the other plate, and that separates the charges in between until they're balanced. So now I know the charge on the equivalent resistor. It's also the charge on each plate of that resistor, or not resistor, sorry, capacitor. And so now I can use this back on my 0.36 microfarad to find the voltage. So I know its charge is 4.944 microcoulombs divided by its capacitance of 0.36 microfarads. So 4.944 divided by 0.36. The micros will cancel, and that leaves me with about 13.7 volts. So because there's a 13.7 potential difference from one side of this to the other, that's the same as from point B to this point on my battery, so 13.7 volts. Now that was all with the switch closed. Now it says find the potential at B after the switch has been closed for a long period of time. Well, let's erase some of this stuff so I can look back at my circuit. With the switch closed for a long period of time, eventually what happens is charge flows off of the capacitors until the capacitors are fully charged, at which point no current flows in this loop anymore because the capacitors are fully charged. So again, this just acts like an open spot on my circuit. There's no current flowing, but now points A and B are actually connected. So whatever the potential difference is between A and the negative terminal is the same as the potential from B to that terminal. And we already know what that is. We know that potential difference is 8 volts. We found that up here in part A. So the potential from here to here, after the switch has been closed for a very long time, is 8 volts. Actually, it's not that long, probably a few seconds. So that 8 volts is part of the potential drop around this loop. That means this other one has to be 16 volts because if we go around the outside loop, the voltage rises and drops, has to be the same. That's Kirchhoff's rules. So 16 volt drop, 8 volt drop, 24 volt drop. Now, we can use that for this last part of the question, which says determine the total amount of charge that moved through the switch. Before the switch was closed, no charge had flowed through the switch. We had a little bit of charge separation from this plate to that plate, but nothing flowed through the switch. Now the switch is going to close, and what we need to know is how much charge is on each plate, and then we got to think about how to combine those. So we know now the voltage across this capacitor is 8 volts. We know its capacitance is 0.36 microfarads. And we also know that charge, Q, is equal to voltage times capacitance. So I can take my 8 times 0.36, and I can say that the charge on each plate of this capacitor is equal to 2.88 microcoulombs. 2.88 microcoulombs. On the other capacitor, the charge on each plate would be at 16 volts times 0.48 microfarads. So 16 times 0.48 is 7.68. So 7.68 microcoulombs of charge. Now, let's think about the charge distribution on here. When these are hooked up and charge is allowed to flow, this is the positive side of that battery, this is the negative side of the battery, and so this is going to push electrons towards here, and it's going to pull electrons off of there. So this is the positive plate, this is a negative plate. The other plate has the opposite charge, so this is a negative plate and this is a positive plate, which means if this capacitor up here is holding 7.68 microcoulombs, 7.68 microcoulombs, and this one down here is holding 2.88, they actually have opposite charge. And so some of these electrons came from this plate. And so we're actually going to subtract these. We're going to get 7.68 microcoulombs minus 2.88 because that's actually the net charge that had to come through the switch. So 7.68 minus 2.88 is 4.8 microcoulombs that actually had to come through the switch.